Can everybody hear me? Okay, good afternoon again. So what I'm going to be looking at are the three methods that we've already talked about. How similar are they to the GMPEs? We talked a little bit about that. We'll get into more in-depth discussion on that. How well is the magnitude scaling constrained? And then I'm going to show you just sort of an overview of what they look like so far. All right, just to back up a little bit, so whenever you see a bunch of charts that are going to be coming up, you'll understand what I'm trying to do. Previously, I showed that this is a magnitude 6.5 with a dip of 45 degrees. These are the station locations. For each one of the stations, there's 32 realizations. And what we do is we take the stations that are within the plus and minus 90 azimuth, source to site azimuth. So we take everything on this side, everything on this side, and then we average these stations. So for the RX of minus 20. Same thing, we take these stations here for the RX of minus 15. They look something like this whenever you take it and look at it in profile. So you can see each one of the 32 realizations, and then I take the average per RX distance. And so the red lines you'll see here, those are the averages. And then you can combine all of the different ones together. And so here I'm showing Graves and Petarka, XM, and SDSU. So you can see the different trends as you're going by. I know a lot of people have not seen how these graphs are made, so I just wanted to spend a second and go over those. Down here is just the dip of the fault. Okay, so just diving right in. The NGA West 2, a couple of the modelers used the hanging wall simulations in order to develop their hanging wall term in NGA West 2. And so based on the Graves and Petarka simulation models that were run in 2011 and 2012, that's what they used to go forward. So what I wanted to give you is an idea of what does the Graves and Petarka 2012 look like compared to the XM and the SDSU methods, because this is what our NGA West 2, some of our hanging wall terms are based on. So if you look, I realize now that I guess the projector is kind of going, it's kind of hard to tell the blue from the purple in the back. Okay. So what I'll just try to point it out as best I can with a pointer. Okay, so the blue dots are the Graves and Petarka. That's what the NGA West 2 hanging wall model for some of the modelers use. So that's the blue line here, and it comes across and it comes back down. This is at 0.2 seconds and 1 second. And so you can see as we're on the footwall, we're coming across and then coming down. XM has a much steeper slope as you're coming up the footwall, much steeper as you're coming down. The purple are the SDSU, so about the same slope, but then they have a little bit more of a hanging wall effect as you're coming over the top. Same thing with the 1 second. The blue, again, that's what we are using for NGA West 2. And then the XM and the SDSU are actually pretty close at further distances on the hanging wall. And then as you're coming up, you are steeper with XM before you start to come down, and then you have, then you're coming off on the other side. Okay, so this was at a magnitude of 6.5 with a dip of 45. This is at 60. So you're starting to see much more of a difference now as you have, this is Graves and Petarka coming up, coming down. XM is much higher. At 0.2 seconds as it's coming up and over the top. And then SDSU is lower than the Graves and Petarka, especially as you're right on top of the hanging wall coming here, and then as you're coming down. So very similar for the 1 second as well. This is for the magnitude 7. So I don't really know what to say about the one on the left. Okay, all right. So Graves and Petarka, again, here's a blue. Again, it's something that we're used to. We're seeing it and it's coming back down the other side. XM, again, steeper slope as you're coming up, steeper slope as you're coming down. You'll see this for the XM for the magnitude 7s, because here we used an RX is equal to 0, and there's something about XM whenever you have RX is equal to 0, it does not handle that very well. What they've recommended is to be at least 250 meters off the fault. So right at RX equal to 0, it doesn't work very well. So this isn't really a true value. It's just what's coming out of the broadband platform. Okay, this is part of the divot that we were talking about earlier. That I have divots and plateaus. You'll get used to how I talk. This is what Doug was talking about earlier, is that you have a divot as you're coming up here on the footwall side. You're coming up, and then you can see that it's very random as you're coming up over the top of the fault before you come back down for SDSU, and this is part of their scattering effect. Same thing on 1 second. It's actually a little bit more contained, and it's coming down. It looks a little better on the 1 second. Okay, the PPRP had requested the long periods, so threw these in at lunchtime so that you can have an idea what they look like. This is at 3 seconds and 5 seconds. Okay, so as Doug was explaining earlier, for Graves and Petrarca and for SDSU, they have the same, the results are the same for the 3 and the 5 seconds, so they're actually plotted on top of each other. But you can see the difference here. XM still has the steeper slopes. They both have a divot right in through here before they're coming up and over. They're slightly flattened out before it's coming back over for the magnitude 5.5 at 45 for 5 seconds. This is at 60, a little bit more well-behaved. But one thing I want you to notice is that it looks, I was going to say it doesn't look, it is. On the footwall side, you can see that the spectral accelerations here look like they are greater than on the hanging wall side, and I think that's where we're starting to get the handoff between directivity and the hanging wall effects, as we're starting to get into these longer periods. Definitely here in the 5 seconds, you know, much higher spectral accelerations, you know, in comparison at the same distance to what you have on the hanging wall side. This is the magnitude 7 with 45 at the long periods. Again, just don't look at that dot. Okay, so this is just to show you what we use for the NGA West 2 hanging wall model. So let's get into how the magnitude scaling effects work. So what you'll see here, there's actually a lot going on. This is the magnitude 5.5, the dip of 45 with the 0.2 seconds and the 1 second. But now we're putting on all of the GMPEs that were talked about by Nick and were talked about by Melanie. So we're looking at the top three, the ASK, the BSSA, Kempler-Besorgnia, Cho-Young's, Idris, Akar et al., J&K, Bindi, and Zhao. So I know that there's a lot to look at, but to sort of get an idea is like when you're on the footwall here, you know, we're matching up pretty well with Graves and Petrarca. These two dots that are here, this is XM and SDSU. So really we're not, Campbell and Besorgnia is a little bit higher, and then you have Akar, which is lower. As you're switching over, you see that we're missing most everything in this area, but we are following the Graves and Petrarca model pretty well because this is at magnitude 5.5. So some of the modelers used stopped at 6, some of them went down to 5.5. So you can see, you know, what the simulations are coming up with in the magnitude 5.5. It's at 1 second over here on the left. Akar is pretty low on the most part. Okay, magnitude 6 at 45. So what we're doing is, as I flip through these are all at magnitude, or the magnitude is going to be shifting, but the dip is going to be 45. So you can see, you know, back here, this is 5.5, going up to 6. Again, as we're coming over, we are matching up with the Graves and Petrarca model fairly well as we're coming back down. This is Idris. He does not have a hanging wall term. He's not looking to capture that. And then as we're coming across the top here, this is DSSA. So they have a plateau, and then they come down on the other side. But on the most part, everybody is fairly well constrained within this side on the hanging wall. A couple of lower ones with Zhao. This is the magnitude 6.5 with a dip of 45 degrees at 0.2 seconds and 1 second, and we're starting to see a little bit more variability. I don't know that much about the G&K method, but I noticed that they do have sort of an M shape through here. They're coming back down the other side. There's something that I need to look at a little bit more. You can see the XM is reaching very high up through, and then comes back down very steeply on the other side. We saw that in some of our other slides. As you can see, here's that BSSA coming straight across. Idris is coming straight down. But you can see that there's This is quite a lot of variability directly over the hanging wall. Same thing on the other side. That was actually hitting up XM really well over here. This is the magnitude 7 at 45 degrees. Again, lots of variability. Everybody looks really good over here on the footwall. Everybody's, you know, it actually looks pretty good. Once you're starting to get to the G&K, Bindi, and Zhao, you are a lot higher. It's actually, and you can see that SDSU is pretty much higher than the other methods. Coming across on the other side, you do have SDSU is higher than most of the other GMPEs. But again, you have a wide variability in the GMPEs, and you actually have a smaller variability within the simulations. This is a magnitude for 5.5 with a dip of 45. This is at the 3 and 5 second. So again, fairly low. And again, Graves and Bitarka and SDSU are going to plot on top of each other. But you can see how much higher they are here than they are for XM. And then most of the GMPEs from NJUS2 are falling here in the middle, except for a couple where you have BSSA that's a little bit lower. But on the most part, everybody's kind of falling between the two sets of simulations, coming up over the top, and basically still within the two. This is magnitude 6 with 45. Again, SDSU is pretty much higher than the other GMPEs. It is following SDSU and Graves and Bitarka are higher, but we are following XM fairly well. We're coming up and coming over to the other side. Same thing here. Magnitude 6.5 with a dip of 45 degrees, and this is where I was telling you that car 13 is looking pretty strange in some of these longer periods with the higher magnitudes. So again, everybody's following along fairly well with XM before it comes up. We're missing the top, so they're coming back down. For the 5 seconds, car is just pretty much flatlined through here. SDSU is higher except for the Zhao model, which is much higher than everybody. But you can see that there is a large variability between the two. And then over here on the other side as well. This is the magnitude 7 at 45 degrees. Sorry, I forgot my little thing at the bottom here. A car is just straight lined across. But you can see that the Graves and Bitarka and the SDSU are plotting much higher than the GMPEs on the most part, and we're still following XM as we go. I threw in a couple of dips of 60 degrees just so that everybody can just get an idea, because I know that most of the GMPs were pretty well constrained with the magnitude 6.5 at 60. This is just to give you a quick idea. This is for the 0.2 seconds and 1 second. So the GMPEs are actually much lower than the simulations. So as you're coming up the footwall, you can see that we're needing a much steeper slope on the footwall in order to get up into the range, where the simulations are a little bit flatter as you're coming up the footwall. Once you get to the other side, XM again is up and down, but as the Graves and Bitarka rolls over to the other side, SDSU is falling off a little bit quicker. And then you have a wide variability, obviously, between the GMPEs, even more so on the 1 second side. And these are the long period. Okay, so what I did next, and this will just take a little bit of explaining, is one of the things that we found for the Graves and Bitarka whenever we took out the footwall and just look at what the hanging wall effect was at that point, we found that some of the maximum accelerations were near the bottom edge of the fault. And so I took the metric at the bottom edge of the fault, looked at the spectral acceleration at that point, and then plotted it up here. So for instance, for the 5.5 magnitude, if you move out a distance, I think it was something like 3.7 kilometers. I'll have to remember what it was, but I think it was about 3.7 kilometers. For the dip of 45 degrees, and looked at what the spectral acceleration was. I plotted that up for each one of the methods there. One caveat is that for the 5.5 and for the 6, Those actually have a depth of 2.5 kilometers because that's what we modeled. We didn't model a surface rupture. Everything that you see basically from the 6.5 over to the right are all surface ruptures. The magnitude 6 with the filled-in dots, those are also with a 2.5 kilometer depth, except for the one open one. Let me explain really quickly about the Graves and Petarka 11 and the Graves and Petarka 12. The Graves and Petarka 11 were the first simulations that were run for the NJUS2 project. And what they did is they did not limit what the width, the down dip width was. They allowed it to rotate from 20 degrees straight down to 70 degrees. They did not modify the length and width. And so what that meant is that whenever you got to a magnitude 7, at a width of 32 degrees, as you're rotating that down, you're getting pretty into the seismic zone. So in the Graves and Petarka 12, they modified the length and the width, keeping the same area, so that as you're starting to rotate down, you're actually making a smaller width but a longer length in order to preserve the magnitude-area relationship. And so whenever we rotated for the Graves and Petarka 12, those larger magnitudes for the 7.5 and the 7.8, the width was fixed at 25 kilometers. So that meant that the length was very long, but for both the 7.5 and the 7.8, it had the same down dip width for 45 degrees. And what we found was that for the 7.5 and the 7.8, it actually turned out to be just about the same spectral acceleration at that point. The Graves and Petarka 11, which allowed a longer width as it rotated down, had a slightly lower spectral acceleration. That's what you can see from the 7.5. For the 7, this was run also in the same fashion. They had the down dip width, I think, was 23 versus 27. And so you can see there that they're slightly different as well. But it was run in what we just recently ran. I think we ran it at 23.8 kilometers. And so, again, you're getting a slight difference in the spectral acceleration, just by modifying the width and looking at what the down dip, looking at the station right over the down dip width. So it actually does make a difference what the width is. So, again, this is something for us to look at for the Graves and Petarka method for sure as you're coming through here. But overall, if you're looking at it for the XM, you can pretty much draw a line straight through here, has a slight upward slope. If you're looking at SDSU and you're going through, it's actually a lot steeper through here. And then if you're looking at Graves and Petarka, it's not quite as steep. It's coming through here, so kind of like the 3 bears. One is steep, one is very steep, one is in the middle. So that's the way that I look at it. So got all 3 there. And this is what it looks like whenever you put the GMPEs on top of it. Again, I took the spectral acceleration at the station directly above the bottom edge of the fault, and so that's what we're plotting here. And so you can see, yes, we do have the trend that's in the upward, but then you're starting to have differences here. So you have a plateau as you're coming out for Idris, who doesn't have a hanging wall effect. You have Campbell and Besorgnia that's coming up and is flatlining as well. You have more of a small plateau over here. This was a car. No, sorry, this is a car. That's Campbell, or sorry, Cho and Young's is here. So with that, are there any questions? And by the way, for those that really know me, I actually have about 400 backup slides that are the other magnitudes with depths of 10 and 20 and 30 and 60. So for those who have sat through the NJUS2, I have all of those as well, but in the essence of time, I'm just showing mainly the 45-degree depth.
So Jennifer, first for the models, I know you rushed to get out something at the longer periods, but the car model doesn't look right. And so
I agree.
I don't think it's plotted right, and you need, while Sinan is here, okay, be sure you talk to him and make sure he corrects it, because something's clearly wrong.
I was going to say, that doesn't look quite right at all.
So let's just get that fixed and not worry about it.
Okay.
I think that it has developed the coefficients up to 4 seconds, right, Sinan?
But even at 3, it looks
Make some brief explanations. Hi, this is Sinan.
Hello.
So we're not considering Z-Tor, firstly, in our model.
Okay.
And also, we don't have hanging wall effects in our model. And tomorrow I'm going to show you about for larger magnitudes, the modeling uncertainty increases in occurrence model.
Okay.
So, I mean, these explanations, I'm sure, will help you in understanding more of the riddle.
Right. But while you're here, let's make sure that we're implementing it exactly right.
All right.
Okay.
Yeah, we can also.
Absolutely.
Okay,
Thank you.
thank you.
So can you go back to your last slide?
Yes.
So the last thing.
Oh, sorry, yes.
Our model is up to 4 seconds. This is also the other.
Okay. Yes. I just blazed on forward. By the way, you'll see that there were not a bendy model at the 3 and the 5 seconds because they don't have a 3 and 5 second either. So they were absent.
So what we were trying to do here was figure out how the hanging wall scaling, if it reduced with magnitude, right? Yes. This is really our fundamental problem. And so we have hanging wall data or some empirical data above 6.5 really, and how do we bring it down to the magnitude 5? And you can see the slopes that people put in, but anything below 6.5 is kind of assumed values, whether it goes out to 6 and comes down or cuts down. If we take all of them together and blur your eyes, then that slope we have isn't too bad, right? But it looks like the SDSU model really has a higher slope on that whole thing. So yes. Is there something, Kim, in your model that you think it would be creating stronger high-frequency effects for the hanging wall? What would be? For larger magnitudes, right? Because it looks really consistent in the 5.5 to 6.5, and then it's kind of still going up a little bit.
I can't think of anything on top of my head. It's always a competition between the longer period deterministic contributions from the low frequencies and the more erratic effect from the high frequency scattering functions. For the higher magnitudes, it seems like the more coherent low frequency contribution is dominating. And that's the only.
This is high frequency.
This is high frequency. So yeah, I can't think of anything from the method that would be creating this at 0.2 seconds. But I will think more about it.
Yes, sir.
I just have a clarifying question. I didn't catch how. So these are spectral acceleration at the bottom edge of the fault. There's multiple points. So how is that averaged?
Okay, so it's still at the RX
along strike.
Right. Yeah, the RX distance from the fault per magnitude. So for 5.5, it was I think 3.7 kilometers, and so those I actually had to interpolate to get to 3.7, and then the next one for the magnitude.
That's for one profile.
Correct.
So maybe part of what could be happening with SDSU is that at this period range, when you look at map view, at this period range, this is Doug Drager, TIT. I'm just speculating here, but so in map view, yes. One of the plots that I showed comparing Graves and Pitarca and SDSU showed that at shorter periods there was more variability. This is essentially across one profile across strike. So is it taking, like, if you made this estimate maybe 5 kilometers north, would you get the same result? Is there averaging along strike? Right.
I haven't gone back, so let me go back to the map. Okay, so this is taking basically between, right, from here, all 32 realizations for each one of these stations and interpolating between the two to get the spectral acceleration at this point.
The bottom line is this is averaged over a whole lot of numbers, right? And so this isn't one realization, it's 30 times your
100
6 or 7 sites, right?
198.
Right.
Yes.
That are averaged out. So this is something that's repeating in the simulation.
I see a hand in the back.
It's okay. I have to make basically the same comment that Akav did a few minutes ago. I'm not completely sure how you applied our model with these comparisons, and I would like maybe have a discussion on this because, again, we also don't have depths to the top of the rupture, and we don't have hanging wall effect.
Yeah.
This is why kind of I would like to continue this discussion because these are very interesting results, but we need to digest them properly.
Yes. Thank you.
It was Vladimir Greiser, NRC.
Thanks. Any other questions or comments? Okay, thank you.